Welcome to AI Paper Slop. For all of you out there building and deploying models, today we are jumping straight into a paper called SenseNova-Vision, Vision as Unified Multimodal Generation.
Right, and this is by researchers from SenseTime, NTU, CUHK, Peking University, SJTU, and Zhejiang University.
Yeah, and the absolute core insight of this, the big takeaway here is that SenseNova-Vision takes the entire spectrum of computer vision and formulates it purely as unified text and image generation.
Exactly. I mean, there are zero task-specific prediction heads.
None at all, which is huge.
Oh, it's a massive shift.
Yeah.
They basically achieve this by using a single unified multimodal model, or UMM.
Okay, so a single model's for everything.
Yeah, so you prompt the model to generate text for symbolic tasks, like outputting bounding box coordinates or camera poses. And then using that identical native generation space, it produces images for dense spatial targets.
Or like depth maps or segmentation masks.
Yeah, and the result is this generalist model that actually matches or beats highly specialized state-of-the-art models like Depth Anything V2.
Wow. Beating dedicated models at their own game.
Right, and it does this across heavily contested benchmarks.
So, to really understand how a text and image generator is beating dedicated spatial regression models, I feel like we need to look at the mechanics of the architecture they are totally abandoning here.
Yeah, that's a good place to start.
Because if you look at standard computer vision pipelines for the last decade, they're built like a Hydra, you know?
A Hydra.
Yeah, like you have this massive shared backbone, usually heavy vision transformer, and growing out of that neck are like a dozen different prediction heads. You have a box head for detection, a mask head for segmentation, a depth head, and so on.
And the fundamental problem with that Hydra approach is mathematical isolation.
What do you mean by isolation?
Well, each of those heads requires its own specific architectural design.
Yeah.
Right, its own loss function, its own decoding logic. So if the backbone learns something highly valuable about spatial relationships while, say, updating weights through the depth estimation head, that localized learning doesn't seamlessly translate over to the object detection head.
Because they're separated.
Exactly. They are completely cordoned off from one another during the final prediction phase. But SenseNova-Vision just eliminates this entirely.
By relying completely on a native generative space.
Right. The model simply responds to instructions. So for symbolic tasks like categorizing objects, outputting spatial references, reading OCR strings, or, defining camera extrinsics, it relies purely on text generation.
And then for tasks requiring dense spatial predictions, so masks, depth maps, surface normals, or dense point maps, it just hands the output over to image generation.
Yep. And the mechanism making that work seems to rely heavily on spatial grid alignment.
So it's kind of like laying a sheet of transparent graph paper over the input image.
That's a great way to visualize it, actually.
The model doesn't have to learn a completely new coordinate system to locate features. It just changes whether it's writing a text token for an OCR word in grid square A4 or shading that exact same grid square blue to represent physical depth.
And maintaining that 2D spatial grid is really the defining structural choice of this whole paper. I mean, we've seen previous attempts at unified vision models like OFA or Pix2Sec.
Right, but they tried to solve this by flattening everything into a sequence format, didn't they?
Exactly. They would take a 2D image or a segmentation mask, serialize it into a 1D string of tokens, and then just ask a language model to predict it sequentially.
Which introduces massive serialization bottlenecks.
Oh, completely.
I mean, if you flatten an 800 by 800 image into a 1D sequence of like 640,000 tokens, the model's attention mechanism has to maintain contextual relationships across impossibly long distances.
Right, just to realize 2 pixels are touching vertically.
Exactly. You just destroy spatial locality entirely.
Precisely. The sequence models get so boiled down because a 1D string simply cannot efficiently represent 2D adjacency. But SenseNova-Vision keeps the 2D grid completely intact.
Because outputs like a depth map are spatially aligned with the input image pixel for pixel.
Yes, so the image generation space naturally sidesteps all those serialization bottlenecks. The UMM possesses powerful visual generative priors. It already knows how to generate coherent 2D structures.
So this architecture just hijacks that native ability to generate dense geometry instead of, standard visual art.
That's exactly what it's doing.
But wait, let me push back a bit on the technical side here. Let's look at the limitations of that discrete image space.
Okay, sure.
Because if you're routing continuous geometric data, like depth maps or surface normals, into a standard 3-channel RGB space, you only have 256 discrete values per channel.
Right, 8-bit color.
Yeah, so how does that not just completely crush the high-fidelity gradients you need for millimeter-accurate depth or precise surface normals?
Yeah.
I mean, we're taking pure floating-point geometry and forcing it into 8-bit color generation.
It's a really valid question, and it was a critical engineering hurdle for them. But the model isn't outputting literal compressed JPEGs for human eyes.
So what's happening under the hood?
During training, they map normalized geometric values, like the continuous X, Y, and Z components of a surface normal vector, directly to the continuous activation space of the color channels.
Oh, before any final quantization happens.
Exactly. The loss functions force the model to understand that shifting the activation in the blue channel directly corresponds to tilting the physical normal vector along the z-axis in 3D space.
That is wild. Okay, so we've killed the Hydra, we have the generative spaces working, but removing specialized heads introduces a massive new problem, right?
The training data.
Yeah. You cannot train a unified architecture without unified data. And traditional computer vision data sets are fiercely siloed.
They really are. You've got depth data sets over here, OCR data sets over there, bounding box data sets somewhere else, and they are all formatted completely differently.
So how did the researchers force all these isolated data sets to speak the same instruction response language?
Well, they constructed a massive conversion pipeline to build what they call the SenseNova-Vision Corpus, or SNVC.
SNVC, got it.
Yeah. They took disparate public data sets and basically reformatted them into standardized instruction response pairs. But simply reformatting wasn't nearly enough because the supervision in public data sets is incredibly sparse.
Right, like you might have an image with perfect bounding boxes, but absolutely no depth map.
Exactly. And to train a model to understand cross-modal relationships, they desperately needed joint supervision.
So they implemented data engines to artificially generate the missing modalities.
Right. So if a data set only had OCR labels, they ran the images through a highly capable specialist depth model to generate pseudo-labels for depth and vice versa.
And they released a subset of this, right?
Yeah, SNVC 50M contains 50 million fully curated examples. The data engine specifically filled in gaps for grounding, referring, B-box to point conversion, and OCR.
And the formatting rules they applied are super rigid, from what I read.
Very strict. Every single training example has an instruction defining the task, the target, and the output schema.
Right, for structured text, they use these lightweight markers, like a P tag for a phrase, followed directly by a B-box tag containing the coordinates.
Exactly.
Now, the text tokenization for standard 2D boxes makes total sense to me, but formatting multi-view 3D data entirely as text seems highly volatile.
It does sound like a recipe for disaster, doesn't it?
Yeah, because multi-view 3D requires predicting camera-to-world extrinsic parameters, specifically rotation and translation, and language models notoriously fail at processing raw floating point numbers.
Right, because standard tokenizers just chop decimals into completely unpredictable subword tokens.
So how do they represent complex Quaternian math and continuous vectors purely in text without the model just hallucinating the decimal placements?
They bypass standard tokenization entirely for geometric data.
Wait, really?
Well, to represent a camera pose, you need a Quaternian for rotation, a translation direction vector, and a scale magnitude, right?
Right.
To map this natively into the text generation space, they actually created a custom dictionary of reserved numerical tokens. And these span exactly from n equals 1,000 to 1,000.
So they hard-coded 2,000 specific vocabulary tokens just to act as discrete integers.
Yes. Then they take all the continuous Quaternian components and translation direction vectors, and they just multiply them by 1,000.
Oh, wow. So that perfectly maps the continuous fractional geometric data onto those discrete whole number text tokens.
Exactly. Instead of the model trying to spit out a messy floating point string character by character and losing the mathematical structure, it literally just predicts the exact integer token from the dictionary.
That's super clever. But wait, the scale of a scene can vary wildly.
Oh, totally.
I mean, a macro shot of a bug and an aerial shot of a city require vastly different translation distances. How does multiplying by a fixed 1,000 handle variance in physical scale?
Good question. For the scale term, they actually decoupled it from the translation vector and constrained the physical range from 0.01 meters up to 10 meters.
Okay, so the token 1 represents exactly 1 centimeter in physical space.
Yes, precisely. And by formatting the data this way, continuous geometric metadata operates seamlessly inside the text space. The model isn't actually performing complex floating point regression,
It's just predicting the most probable discrete token in a highly structured sentence.
which language models are exceptionally optimized to do.
Right. So with the data successfully unified into these native formats, let's talk about the sheer scope of the tasks this single model is processing simultaneously.
Yeah, the scope is massive. The researchers divide the model's capabilities into 4 distinct families.
Okay, break those down for us.
First up is structured perception, which handles your standard bounding box detection, layout analysis, GUI understanding, and OCR. Second is dense geometry, handling depth and surface normals. Third is segmentation, covering referring, general, and interactive segmentation. And the final family is multi-view 3D.
I want to zoom in on that multi-view 3D capability because it is particularly dense. It's like giving the model a stack of flat vacation photos from different angles of a scene.
Yeah.
And in a single forward pass, it generates the text tokens detailing the exact camera-to-world extrinsic angles for every single photo, while simultaneously outputting an image tensor where the pixels represent a dense XYZ point cloud of the entire 3D environment.
It's incredible. The model is explicitly trained to perform interleaved text and image outputs.
So it's not just doing these tasks in isolation.
No, it aligns its textual reasoning with its spatial rendering on the fly. And because the OCR, depth estimation, segmentation, and camera poses are all trained jointly on the SNVC corpus, we actually start to see emergent cross-modal correspondences.
Meaning the model is discovering latent alignments between modalities that it was never explicitly programmed to connect.
Exactly.
What's the mechanism behind that emergent behavior? Give me an example.
Consider zero-shot text segmentation.
Okay.
So the model is trained on OCR, which involves drawing a bounding box around text and transcribing it into string tokens. Separately, it was trained on segmentation, generating a pixel-perfect mask around the contours of physical objects.
Right, but the dataset never contained training examples where masks were explicitly drawn around individual text characters, did it?
Never.
Yeah.
Yet, because the text generation space and the image generation space share the exact same underlying representation in the UMM, you can literally prompt the model to generate a mask for the word Coke written on a soda can.
Oh, wow. So it leverages the localization weights it learned from the OCR training.
Yes.
Routes that positional data through the latent space, and then applies the boundary rendering weights it learned from the segmentation training to draw perfect masks for the letters C, O, K, and E.
Exactly. It dynamically recombines isolated skills to solve a zero-shot physical task.
That is the defining advantage of unified representation right there.
Totally. But, as you know, the ultimate test for ML engineers is whether this generalist architecture actually holds up on specialized benchmarks.
Right, because historically, consolidating tasks into a single model usually results in a performance penalty. The model becomes a jack of all trades, but a master of none.
Not in this case. SenseNova-Vision doesn't just participate, it dominates.
Let's look at those benchmark numbers, because this is where the paper challenges the necessity of specialist pipelines entirely.
So in dense geometry, tested on the NYU V2 depth estimation benchmark, SenseNova-Vision achieves a 98.1 mean delta 1 score.
And for those unfamiliar with the delta 1 metric in depth estimation, it essentially measures the percentage of predicted pixels where the relative error between the prediction and the ground truth depth is less than 25%.
Exactly.
So 98.1% of its depth predictions are within the strictest margin of error for real-world geometry. How does that compare to the heavyweights in the specialist category?
Well, Depth Anything V2, which is a highly specialized model dedicated exclusively to depth, hits 97.8 on that exact same metric.
Wow.
Yeah. SenseNova-Vision also outperforms Mode 2. And to squeeze out a 0.3 margin at the absolute asymptote of performance is notoriously difficult.
So a generalist text and image model outperforming the most tuned specialist models in their own domain proves the architecture is not sacrificing precision for versatility.
Not at all.
Yeah.
And across the other families, the results show a very similar dominance. In structured perception, it achieves a 53.7 mean average precision on the COCO object detection benchmark.
That's massive. How does that stack up against other generalists?
If you put that up against other generalist visual models like U2VL, which scored 47.1, SenseNova-Vision is vastly outperforming the generalist competition as well.
And it remains highly competitive in reasoning segmentation against models like LISA and holds state-of-the-art status in multi-view 3D reconstruction.
It really does.
But, let me push back a bit beyond the standard leaderboards.
Sure, go ahead.
If I'm building an AI product, benchmark scores are only half the equation. I want to know if this generalist approach actually yields novel, free-form behaviors that a traditional specialist pipeline simply cannot execute.
Okay, I see where you're going.
Yeah, so if I'm giving this model an image of a complex scene, I'm assuming I don't just prompt it with the word segmentation. I'm guessing I have to natively speak to it using syntax and specific rendering parameters.
Yes, and that is exactly the killer application of this architecture. Free-form language-to-mask generation.
Okay, how does that work?
You can dictate the exact rendering parameters in line with complex textual reasoning. Imagine providing an image of a crowded beach. You can feed the model a prompt, like the sky, color code 12680-254, is visible over person 2, color code 791455.
Wait, really? So you're demanding that it reads the scene, tracks the physical relationships between the objects, identifies the specific instance of person 2,
Yep.
and then renders a pixel-perfect mask using the exact hexadecimal color codes you provided right there in the text instruction.
That's exactly what happens. It parses the syntax, grounds the objects perfectly, and outputs the color-coded segmentation mask in one step.
That's incredible. A traditional specialist pipeline fundamentally cannot compose these distinct modalities on the fly.
Right. A standard segmentation model has absolutely no mechanism to parse syntax or interpret hex codes. And a standard large language model has no mechanism to output a high-resolution spatial pixel mask.
To achieve that with a traditional architecture, you would have to build a really complex multi-stage pipeline.
That'll be a nightmare.
Yeah, you'd pass the image to an object detector, send those coordinates and the prompt to an LLM to assign the hex codes, pass that structured output to a segmentation model, and then compile the final mask.
And it would be slow, brittle, and highly prone to cascading errors. Where a failure in step 1 just totally destroys the output of step 3.
Exactly. But SenseNova-Vision executes the entire reasoning and rendering chain natively in a single forward pass.
Because the text understanding and the image generation spaces are fundamentally unified.
Which brings us to the ultimate conclusion of this deep dive. We have spent years building a Hydra, carefully engineering mathematically distinct heads to solve very specific visual problems.
And SenseNova-Vision proves those heads are actually a bottleneck.
Right. By leveraging the curated SNVC 50M corpus to force heterogeneous data into a standard instruction format, native text and image generation spaces are entirely sufficient.
A single unified model can conquer everything from standard OCR to dense multi-view 3D point clouds, matching or beating the best specialist models in the world.
It's a massive shift for the field.
It is, and this research poses an almost existential question for the immediate future of machine learning.
Which is?
Well, think about it. If we can represent multi-view 3D point maps and complex fractional camera extrinsics simply as multimodal text and image tokens, what happens when we scale this exact formulation to continuous temporal video streams?
Oh, wow.
Or what happens when we map physical robot action sequences, like the joint angles of a robotic arm, to these discrete integer tokens? Will the very concept of a dedicated computer vision model completely disappear within the next 2 years, swallowed entirely by generalized foundation models?
I mean, if an XYZ coordinate can be accurately mapped to RGB pixels, then a robotic actuation can just as easily be a text token. It's wild to think about.
It really is.
Well, thank you all for joining us for this analysis on AI paper slop. We highly recommend pulling up the full SenseNova-Vision paper to examine the data engine methodology and that Quaternian mapping for yourself.
Definitely worth a read.
Until next time, keep building, keep researching, and we will see you on the next deep dive into the research.